My name is James Carl, and this is Lab 3. The purpose of this lab was to calculate the mass of the black hole using a star's positional orbit around the black hole. We'll use Newton's first law and Newton's second law. Using the data given to me, I created a program within IDLE so that I could determine the mass of a black hole and visualize the path of the star. First is Newton's law of force, which shows that F net equals gravity times the mass of the star multiplied by the mass of the black hole divided by the radius squared, where the G equals 6.67 times e to the negative 11 newtons. F net is derived by Newton's second law. We will get everything used in the formula by using the position data of the star moving around the black hole. Using the data, we found the velocities. Then using the velocities, we will find the momentum and then continue on to break up the momentum into its parallel and perpendicular components to find total F net. We will use this formula and put it into VPython to create a computer model where we can then measure the mass of the black hole. Some of the important things to know for this lab are the meanings of F net, the parallel and perpendicular components of F net, dp/dt, and the parallel and perpendicular components of dp/dt. Here is how F net and dp/dt equal each other. But really the biggest difference between these things is what essentially they are. F net cannot be calculated, whereas dp/dt can. F net is qualitative, dp/dt is quantitative. The important thing to look at in this experiment is the code that I changed in order to make the program work for me. The first thing I worked on was making sure that I could visualize the black hole in which the star was interacting. Then I entered in the mass of the star into the code here, put the position of the black hole next, and placed the gravitational constant in. Next I put the time of 86,400 as delta t because that represents a whole day in seconds. Then I worked on the x and y components of the velocity of the star. I set up a time scale for the y component of the velocity, then made the y velocity equal to delta y over delta t. Next I made the changes in order to calculate the net forces from the motion data. Within this while loop, I made first 2 lines of code for v initial and one for v final. Next I computed the initial and final momentum vectors, here. Then I made the necessary changes to the code to solve for the star's change in velocity and change in momentum. I set delta v equal to v final over v initial and delta p equal to p final over p initial. I then put in the code for the formula of dp/dt, which is equal to delta p over delta t, and set f net equal to dp/dt. I then moved on to calculate the parallel component of dp/dt. I set p hat equal to p initial over the magnitude of p initial. Then I set the derivative of the magnitude of p over dt equal to the magnitude of p final minus the magnitude of p initial over delta t. Then I used Newton's second law to know that the parallel component of F net equals the parallel component of dp/dt. I then solved for the perpendicular component of dp/dt by subtracting the parallel component of dp/dt from dp/dt. Then I set the perpendicular component of F net equal to the perpendicular component of dp/dt. For this next part of the code, I set the arrow scale of my arrows in my VPython diagram equal to 9.9 e to the negative 16 because I felt that it gave a good representation of the forces. Lower in this section of code there is a place where I placed the law of gravitation. I set the mass of the black hole equal to the gravitational constant times the mass of the star, then multiplied by the magnitude of F net times the magnitude of the star's position minus the black hole's position squared. Toward the bottom of this section of code is where I put the code to print out my desired values of time, the magnitude of F net, and the magnitudes of the perpendicular and parallel components. Also, I asked the program to spit out the value for the mass of the black hole. Now that you know the different ways I turn the formulas we know into code, let me show you the result. Here is my video. As you can see, the orbit that was given to me was small, but I used the orbit to calculate the mass. The black arrow was the parallel force, the blue arrow was the perpendicular force, and F net was the yellow arrow. And as the star moves, the arrows show the forces acting on the star. At the end of the program, it displays the things that I asked for at the end of the code. The most important, which is the mass of the black hole, which turns out to be 3.58 e to the 31. Very heavy. Here's the what if. I was asked to imagine that if I had just the path of the star and the star's mass, if I could tell if there was a difference between a new black hole or an old black hole, the one that I calculated. I concluded that there would be no difference, because in order for the path of the star to remain unchanged, the mass of the black hole would have to be the exact same as the early one. You can do this by checking me if you want to, but basically due to the law of gravity and the gravitational constant, where the mass of the star is the same and the path doesn't change, the black hole would have to have the same mass. So basically the answer is no. You could not tell the difference. In this lab I determined that the mass of a black hole could be determined from a path of a star over the period of one day using idle NVPython.